Welcome to Asgardians TechX, the online channel for your daily science and technological news, trending topic and update about the future of humanity, space, agriculture and science at large. Please before watching don't forget to subscribe, like and comment on my channel on how to improve it, and on topics which you want to hear more about. A California startup has developed and tested a prototype of a lunar rover that it plans to offer to NASA for use on future Artemis missions. Venturi Astrolab revealed March 10 its work on a rover called Flexible Logistics and Exploration, or FLEX, that is intended to carry cargo or astronauts. The rover is designed to accommodate up to 1,500 kilograms of cargo, placed above or below a main deck, and either be driven remotely or by two astronauts on board. Jarrett Matthews, founder and chief executive of Astrolab, said in an interview that his company created Flex to address a near future of lunar exploration where both crewed landers like SpaceX's Starship and robotic landers for NASA's Commercial Lunar Payload Services program deliver large amounts of cargo. Flex really represents a rethinking of how you might approach the surface in that context, he said. We're making Flex to be the most versatile rover ever created, and the primary innovation is the fact that we have this modular payload capability. He contrasted Flex with past rovers, like those developed for robotic Mars missions, that were customized for their specific missions. He worked on several Mars rover programs at the Jet Propulsion Laboratory earlier in his career, as well as a concept for a lunar rover called Athlete during the Constellation Lunar Exploration Program. That is a reasonable approach in an environment where you have an extreme emphasis on mass efficiency, he said of those earlier designs. But in this coming era of more lander capability, what we're doing is thinking more about economies of scale that you might achieve if you rethink that approach. Flex is more than a concept. The company built a full-sized prototype of the rover and recently tested it near Death Valley, California. They simulated using the rover for a range of activities expected for a future lunar base, such as setting up solar arrays, as well as its ability to navigate terrain either with people on board driving it or through teleoperation. Among those who drove Flex in the test was former astronaut Chris Hadfield, who emphasized in a statement the value of mobility for future long-duration lunar exploration and settlement. It was not only a joy to drive Flex but also see its size, capability and get an intuitive sense of what this rover can do, he said. He was a great fit for us, Matthews said of Hadfield, citing the former astronaut's experience that included serving as chief of robotics in the NASA astronaut office. He really gets what we're doing and the potential. Matthews said Hadfield and others provided invaluable feedback on the Flex prototype, offering suggestions on changes to rover controls. The intent was building the prototype quickly, so that we can start learning and be ready as soon as the first opportunity to go to the moon comes up, he said. Augmented reality (AR) is an interactive experience of a real-world environment where the objects that reside in the real world are enhanced by computer-generated perceptual information, sometimes across multiple sensory modalities, including visual, auditory, haptic, somatosensory and olfactory. AR can be defined as a system that incorporates three basic features: a combination of real and virtual worlds, real-time interaction, and accurate 3D registration of virtual and real objects. The overlaid sensory information can be constructive, i.e. additive to the natural environment, or destructive, i.e. masking of the natural environment. This experience is seamlessly interwoven with the physical world such that it is perceived as an immersive aspect of the real environment. In this way, augmented reality alters one's ongoing perception of a real-world environment, whereas virtual reality completely replaces the user's real-world environment with a simulated one. Augmented reality is related to two largely synonymous terms: mixed reality and computer-mediated reality. The primary value of augmented reality is the manner in which components of the digital world blend into a person's perception of the real world, not as a simple display of data, but through the integration of immersive sensations, which are perceived as natural parts of an environment. The earliest functional AR systems that provided immersive mixed reality experiences for users were invented in the early 1990s, starting with the virtual fixtures system developed at the U.S. Air Force's Armstrong Laboratory. In commercial, augmented reality experiences were first introduced in entertainment and gaming businesses. Subsequently, augmented reality applications have spanned commercial industries such as education, communications, medicine, and entertainment. In education, content may be accessed by scanning or viewing an image with a mobile device or by using markerless AR technique. Augmented reality is used to enhance natural environments or situations and offer perceptually enriched experiences. With the help of advanced AR technologies, e.g., adding computer vision, incorporating AR cameras into smartphone applications and object recognition, the information about the surrounding real world of the user becomes interactive and digitally manipulated. Information about the environment and its objects is overlaid on the real world. This information can be virtual. Augmented reality is any experience which is artificial and which adds to the already existing reality or real, e.g., seeing other real sensed or measured information such as electromagnetic radio waves overlaid in exact alignment with where they actually are in space. Augmented reality also has a lot of potential in the gathering and sharing of tacit knowledge. Augmentation techniques are typically performed in real time and in semantic contexts with environmental elements.
C2, an upcoming all-electric hypercar that's projected to hit 0 to 60 in just 1.85 seconds. And this is one smashing headfirst into a wall. Just like any other car, the C2 has to be crash tested before all 150 units can be manufactured and sold. But how do you crash test a hypercar without losing millions of dollars?
Developing a very expensive low-volume hypercar is not that different from a high-volume family vehicle when looking at the safety. So we have basically to do the same tests, which means hundreds and hundreds of tests, or actually thousands of tests. The problem is, with the low-volume production that we have, it's hard to justify to produce many cars in the testing phase. Actually, big car companies would produce the same amount of cars that we will produce in total for customers and everything included just for their testing program. We have to condense that to fewer vehicles, 12 cars in different stages of development.
So, how does Rematch make just 12 cars last hundreds of tests? The C2 is built around a carbon fiber monocoque. This means its backbone is one giant carbon fiber cell that houses the passengers. This much safer and reliable design has quickly made its way into modern hypercars like Bugatti and Koenigsegg. Rematch claims its monocoque to be the stiffest structure ever put in a road car, tougher than a Le Mans race car, and 3 times as strong as a traditional road car. The C2's monocoque is surrounded by aluminum crash structures in the front and rear. Crash structures, or crumple zones, are the sections at the front and rear of the car designed to absorb as much of a crash impact as possible before it reaches the cabin. A majority of crashes, including those Rematch performs during testing, only these aluminum parts are affected and can easily and affordably be replaced right away. The battery pack is also a structural part of the car that sits in the middle of the monocoque. It would require an accident far beyond what's tested here or at a third party to damage the battery.
So you might think that maybe the crash test cars cost a lot less. Well, actually, as they are prototypes, and there's lots of parts made in a way that are not, let's say, production spec, and you have a lot of special tooling and 3D printing and stuff like that, it's actually more expensive to crash those cars and then replace the parts over and over again after every test, that each crashed car is actually more than 2 million.
So what does the crash test process look like? The first phase is done using computer simulations. Here, the team can really go wild, experimenting with all kinds of vehicle layouts and materials. As a multi-million-dollar car, the C2 requires hundreds of simulations before engineers settle on a design. Once a design for the car's frame and chassis has been chosen, physical tests can begin. The car's crash structures are put on a sled and rammed into a wall. The team looks to make sure the vehicle's build and the materials are suitable. Once enough data is collected and engineers are satisfied, it's time for the next phase, testing prototypes. In the first test, electronic components are replaced with dummy parts of the same size and weight to keep results accurate and cost low. Using data from these tests, the team develops a prototype with a fully functioning drivetrain. These cars will be crashed at higher and higher speeds, from 10 to 50 miles per hour, until they are ultimately destroyed. Rematch uses prototypes that only have the front or rear bodywork of the car attached, in order to save time and money. These prototypes are what engineers hope to use for the final production. Only after the team approves of this model can they begin homologation, where fully completed cars are tested in front of third-party authorities, who decide whether the vehicle meets safety standards. By now, Rematch has reached the homologation phase, and it won't be long before the C2 is street ready. But no matter how safe and technologically advanced Rematch can build the C2 to be, watching a $2 million car get smashed to bits will always be painful.